Alcohols can undergo substitution reactions when treated with strong acids if the conjugate base of the acid is an effective nucleophile. But alcohols can also undergo reactions with concentrated acids like sulfuric and phosphoric acid, where the counterions are not good nucleophiles, to result in E1 elimination products. So, for example, cyclohexanol, when treated with a mixture of concentrated 71% phosphoric acid and concentrated 98% H2SO4, both of these are concentrated acids, to result in cyclohexene. In this particular case, only one alkene product is possible, so we don't have to worry about whether we get the Sacef or the Hoffman product. But since this is an E1 elimination, when there is a difference, we will always get the Sacef product. The reaction proceeds in much the same way as the reaction with concentrated hydrochloric or hydrobromic acid. We have hydronium ion present, because the rest of the solution that isn't phosphoric or sulfuric acid is water. We'll protonate in an equilibrium process to generate the alkyl on sodium ion. But now, after the leaving group leaves in step 2, generate a carbocation. Instead of being trapped by a nucleophile, water will come and remove an adjacent hydrogen. To regenerate the acid catalyst. It's usually catalytic in sulfuric acid, with the bulk of the material being the concentrated phosphoric acid, because sulfuric acid tends to be a unstable material that results in really dark brown and black products if you use just the concentrated sulfuric. It is normal to heat this, because by heating it, we increase the entropy of the system, or we increase the extent to which the entropy matters, and you'll notice that the overall balanced reaction forms two molecules from one, which means that it will be entropy favored. Generally, entropy favored reactions are run at elevated temperatures. So it's a 3-step mechanism, just like the other one. At 1, protonation. At 2, loss of the leaving group. But step 3 now is deprotonation instead of nucleophilic action. And the reason for that is that dihydrogen phosphate ion and hydrogen sulfate ion are both very poor nucleophiles. As well as being very weak bases, very poor bases. So they're not effective as Bronsted-Lowry bases, and they're also not effective as Lewis bases for nucleophiles. So these ions will just sit around rather than attacking positively charged carbocation, and water will act, in this case, as a base. The entire process is in equilibrium. It is, in fact, possible to hydrate alkenes to form alcohols, and we'll see that reaction later in chapter 12. But for now, when we're working with concentrated acids, the reaction at high temperature tends to push over towards the alkene as the product because of entropy. If you have an alcohol that could eliminate in 2 different directions, it leads to PO4 and concentrated H2SO4 catalyst, can result in 2 possible alkenes. The Sacef product being more stable Trisubstitute alkene. Will be the major product. And the Hoffman product being less substituted and less stable vinyl group will be the minor product. An alkene that has 3 hydrogens on it, like this, is referred to as a vinyl group. If you put a chlorine on here, it's vinyl chloride, which is the monomer that produces polyvinyl chloride, or PVC. So this vinyl group is monosubstituted alkene is significantly less stable than this. Conjugation is the reason for that as well. The more hyperconjugation we can have from the adjacent sigma bonds, the more electron rich we can make this pi bond, and pi bonds benefit from electron donation to make them better bonding. There's actually 2 different potential mechanisms that you could propose to generate this Sate-Seth product. One of them is directly analogous to what we've seen over here. The first step would be coordination. The second step would be loss of water. For those 2 steps, nothing changes. And we generate a secondary carbocation. If water comes in from the tertiary position, we would now get the product that we expect in the third step. That mechanism is identical to the mechanism shown for the cyclohexanol. But there's an alternative mechanism, because this intermediate is also capable. Redraw the intermediate. Of undergoing a hydride shift to generate the more stable tertiary carbocation. It won't look a lot different, but you'll notice that when I'm actually doing an elimination, I take the arrow from the bond between the carbon and hydrogen to the center of the bond, because it's going to be forming a pi bond in the product. I show the arrow pointing directly at the carbon, because the hydrogen is going to be bound to that carbon. That's a hydride shift. It results in the tertiary carbocation. And now if water comes in and removes one of the 2 hydrogens from the secondary position, note that this arrow goes from the middle of the bond to the hydrogen to the middle of the bond between the 2 carbons, where it's going to be, then we will get the same Sate-Seth product. So there's 2 different ways that product could be generated. You might predict that a third product that I didn't draw initially could form, because once you've had this hydride shift to generate the tertiary carbocation, there are now 6 adjacent hydrogens attached to the 2 methyl groups. And if any of those are removed, a third product, a di-substituted alkene, should result. And this di-substituted alkene should be more stable than the vinyl group. So we would actually expect this product to also be present as a minor product. Still, the Sate-Seth product will be the dominant product because it's the more stable alkene. And since all of these processes, with the exception of the hydride shift, are equilibria, you would expect eventually the more stable product will be the major product. Because in a reaction like this, it's under thermodynamic control. Product stability is what dictates which product is formed. So as we've seen, any time a carbocation is formed, carbocation rearrangement through hydride shifts or alkyl shifts is possible. If you want to avoid hydride shifts and thus carbocation rearrangements, you have to make sure you don't form a carbocation. It's not possible to hold a sign outside the reaction saying, please don't rearrange. The carbocation is going to rearrange if it thinks it can become more stable by doing so. So I mentioned in the previous video that in addition to alkyl shifts and hydride shifts, we can have ring expansions and ring contractions. Consider 2,2-dimethyl cyclohexanol. Treated with 71% phosphoric acid and 98% sulfuric acid. And heat. Usually you just boil it. Not surprisingly, the first thing that's going to happen is to protonate the alcohol. To generate an effective leaving group. As always, that reaction is equilibrium. Water can then leave, taking its electrons with it, to generate a secondary carbocation. And at this point, we can, in fact, have a methyl shift to generate the more stable tertiary carbocation. Notice that the carbocation is on the carbon that the methyl group is not shifting to. Right? This methyl group has just moved. So now we have trigonal planar tertiary carbocation there. And one possible way that that could eliminate would be to take the hydrogen off that just moved to generate a stable tetrasubstituted bond. Cyclohexene. But that's just one possible pathway. There are numerous other possible pathways and numerous other possible products, one of which would stem from the same carbocation so we eliminate a hydrogen from the left-hand side, the CH2 group, rather than the CH group. To generate a different alkyl group. Sorry, this is not cyclohexene. For some reason I made those into hydrogens. This is 1,2-dimethyl cyclohexene. This is another cyclohexene, and we would number it this way. We want to number so that the double bond has the lowest number possible, and we want to number it in such a way that the more substituted end of the double bond has the lowest number possible. And then we need to number it so that the second carbon is in the same, is attached to the double bond. So this would actually be 1,7 dimethyl cyclohexene. It's less stable because it's tri-substituted instead of tetra-substituted, so we would expect it to be present in smaller quantities than the 1,2-dimethyl cyclohexene. The secondary carbocation is shown here, though, in other ways. And one of the ways it can rearrange is by moving the bond, carbon-carbon bond of the ring, and transforming the less stable 7-membered ring to a more stable 6-membered ring. That's a ring contraction. It's an alkyl shift. And it will be associated not only with a switch from a secondary carbocation to a tertiary carbocation, but also with a release of some of the ring strain, because the 7-membered ring is less stable than the 6-membered ring. I find that to avoid messing up, the best thing to do when you're doing a ring contraction like this is to write the same molecule without moving any carbons, and then erase the bond and move it to the new position. And then we can redraw that so that it looks more like a 6-membered ring, but without risk. So we've got a more stable 6-membered ring. And we've got a more stable tertiary carbocation. That tertiary carbocation can now eliminate to generate additional alkene products. So we can take a hydrogen off. To generate isopropylene group here, 3-membered ring, or three carbon attachment, which is a tetra-substitute double bond and should be quite stable. We could eliminate from that same carbocation by removing one of the hydrogens from the methyl group. There are 6 identical hydrogens that could do that. That wouldn't be expected to be a very large contributor because it's a less stable disubstitute double bond as opposed to the tetrasubstitute double bond. And we can also get another product isopropyl cyclohexene. Or 1-methyl ethyl. Depending on whether you want to use the common name isopropyl or the IUPAC for isopropyl 1-methyl ethyl. And you could ask yourself the question, where did that come from? Well, you notice that this tertiary carbocation has branching in the beta position. If instead of water removing this hydrogen, the hydrogen just shifts. Redraw that. So it's a little easier to see. The hydrogen shifts. We can generate a different tertiary carbocation. These tertiary carbocations would be expected to be of similar stability, except that when you consider that removing a hydrogen from the ring will reduce the 1,3 diaxial interactions, having a carbocation in a six-membered ring like that is quite stable. After all, the preferred bond angles for a regular hexagon are 120 degrees, which are the angles you're going to see on a trigonal planar carbocation. So this carbocation is quite stable and can lead to either of these two products, depending on whether you remove the hydrogen that you just had in the shift, or whether you remove an adjacent hydrogen to form the tri-substituted ring. And all of these reactions are going to be equilibrium. So what we would expect is that our major product will be the most stable of all of these possible products. Because product stability is what you should see is what you should use as a deciding factor when you're working with a reaction that's under thermodynamic control, and all reactions that are under equilibrium are under thermodynamic control. So in this case, we saw a ring contraction from a 7-membered ring to a 6-membered ring, but it's equally likely to see a ring expansion if you have a strained 3 or 4-membered ring that could expand and reduce ring strain, reduce bond angle strain that way. And you'll see one of those in one of the homework